of the Institute. And my duty here is just to welcome you all. For some of you, welcome to Brazil. For many of you, welcome to Natal. And for everybody, welcome to the Institute. Let me tell you that all our meetings are taped and transmitted online. And if you don't like the idea, just make a sign-on. It's in the backstage, and they will shut off the cameras. Other than this, if you have any questions about the city or where to go, what to do, I will say first is the workshop. But I think there are lots of attractions in the city. So please, you can report to the registration office. You have been there already. And talk to the boys there, and they will give you some hints about this. So once again, thank you for being here, and let me thanks to the organizers in the person of Professor Vanderlei and to all the speakers of this meeting, and mailing to all of you. So welcome to the Institute. Vanderlei now is in your hands.
Okay, so good morning to everybody. David and Giorgio, we should come here. In fact, this is a workshop that was proposed by Giorgio and David, and it is a kind of traditional in Europe to have this kind of more than just a few days type of meeting, where we're supposed to deal with a topic like this one that's still a challenge, right? It's an old and still big challenge topic. And we thank you all for coming. I guess David and Giorgio will give you some more words after that. I just want to tell you that the first week is more or less dedicated to like a school. And we brought more students and postdocs that are in the topic. And then the second week is supposed to be the workshop. And in between, we should discuss everything we want. So thank you for coming. And I guess David and Giorgio will give some words and thank the speakers and explain the program. And during the workshop, we're going to give you small words, some announcements about what to do, how to go, and so on.
Well, thank you, Vanderlei. Thank you all for coming. Yes, the idea of this first week is to have this summer school, but also to leave plenty of space slots free for discussions and group work or presentation of maybe some ongoing work that you've been doing, open questions, and or just time for you to continue working here at the Institute. And we're going to have every day an average of 3 lectures, except today we're going to have 4, I think, if I remember. And then we're going to have a couple of invited talks per day. But if you would like to maybe give a short talk or discuss on a particular problem, let's just organize that maybe day by day and make it informal. So even if you don't have slides which are ready, it's fine. That's more or less the spirit of the first week.
Yeah. So if you brought poster, please yes, hang it as soon as you can, and we can try to discuss about them in a very informal way. Okay, and I don't know what else to say.
Well, they should leave the posters on all the time, because the coffee breaks will be exactly in front of the posters. It's a good opportunity to talk and to discuss. Okay.
Yeah, one important thing, especially during this week, please don't hesitate to raise questions. Even if you think that may be stupid, certainly they won't. And the goal of this week is just to discuss and enjoy And so please don't be ashamed of asking anything you want.
Okay. So
I think it's time to...
it's time to start. So maybe, I guess, Carlo Barenghi is a scientist that does not need a big introduction. But it's nice to introduce the speaker, right? So Carlo is an Italian physicist that is basically living in England, in Newcastle. And he's one of the authorities in the field of quantum turbulence, with many papers, many ideas, and even a book, which I recommend you. I don't know if it is still available, but I remember there was one time that you sent the PDF of the book. I don't know if still is the case, but for people like the ones that are here that are like start experiments or theory in this field, it's good to have the book of Carlo Parker. So Carlo is giving lectures, and the battery is going on out of this microphone. And since it's supposed to be tutorial lectures and everything, everybody should be encouraged to, as Giorgio and David said, stop and ask questions during. We're all going to learn with the questions, right? So thank you all for coming. And there is a last thing is on Thursday, there will be a group meeting. We're going to, a group photo. So we have on Thursday is when many people from the second week are arriving. So we're going to have a first photo, and then next week we have a second photo, and then we try to combine both and make sure that everybody's in the picture. So thank you all for coming, and if you have any question, people here, we're not a large group, and people here is very well prepared to help us with everything we need. You realize that we are far from here with the hotel, so every morning we come, every afternoon we go, end of the afternoon. And lunch is served here. They have a restaurant that we're going to have lunch, and it's another opportunity. And the speakers, if they need an office, there are offices available for everybody. And internet supposed to be everywhere, so thank you.
Okay, thank you, Vanderlei and Giorgio and Davide. Can you hear me? So I'm going to tell you something about turbulence in quantum fluids. And I was not really given instructions about the background and how I should pitch this presentation. So I assume that perhaps you have, at least most of you have more of a background in atomic physics than fluid dynamics or low temperature physics. Therefore, I'll try to fill the gaps, because I'm keen to present the problem of turbulence in a quantum fluid in a way which brings together work done in various disciplines like atomic physics and low temperature physics and also fluid mechanics. So in summary, these are the topics which I'm going to touch in a very, very simple fashion. So I'll start to keep things as easy as possible, as simple as possible, historically, and I'll try to present lots of pictures. Hopefully you will remember the pictures, and you can fill in the details and the difficult equations later, because there will be some lectures about details. So this morning I have a slot of 2 hours. Perhaps I'll take a break after the first hour. So you see, essentially we're progressing from some historical introduction to a description, generic description of quantum fluids and vortices, and then a review what are basic ideas about turbulence, and then apply them to quantum turbulence. So let's start from the history. So most of these subject is related to the history of low temperature physics, and that is I want to introduce. And my story starts with an instrument maker in Paris called Amonton, who at some point of his life had a good idea of measuring the pressure difference induced by temperature differences in a gas. And he thought that the pressure could not become negative, and extrapolated, therefore, a minimum value for the temperature. And this extrapolation in modern units would correspond to 240 degrees below zero, centigrade degrees below zero. So this is how the history of absolute zero starts. About at the same time, slightly later, the Swiss mathematician Bernoulli, Daniel Bernoulli, there was a family of mathematicians, also thought of that, and he believed in the existence of atoms and essentially small particles colliding, and he thought that somehow perhaps the temperature has to do with the motion of the atoms. So essentially no motion means no temperature. So that was again a very good idea, but unfortunately this good idea was put to rest for many decades because of the success of a new discipline which was born, chemistry essentially, and the great chemist Lavoisier, who had his own theory of heat, which was wrong. Oops, lost the thing. So sorry. Yeah. But in the 19th century, these ideas about atoms and temperature went back to the track, and they proved very useful. So let me remind you of how we define the temperature nowadays. So we use the temperature based on Kelvin degrees, and there are essentially three well-known temperature scales. So we have the Fahrenheit scale. So there water boils at 212 Fahrenheit degrees and freezes at 32. So Fahrenheit essentially invented the idea of this temperature scale, and he thought that he should have two reference points. He took one, understand was essentially the temperature of the coldest night. He lived in northern Germany, or perhaps Poland, I'm not sure. And the temperature of the human body was another reference. So those are not actually values which can be produced easily. So clearly progress was made later when a Swedish scientist called Celsius thought of using the freezing point of water and the boiling point of water as a reference. So he took 100 degrees for the freezing point of water and 0 for the boiling point until Carl von Linné, or Linnaeus, who was the essentially great botanist, inventor of how we classified species, told him, oh, well, that's just rubbish. Why don't you do the other way around? If it is hot, it is bigger number. So since then, we've had this scale. 100 degrees is the boiling point of water, and 0 is the freezing point of water. And then there is a third scale, the Kelvin scale. Now, the Kelvin degree is the same as the Celsius or centigrade degree, but rather than starting with the freezing point of water, we go to the absolute 0, because now this idea was taking hold. And the other thing which was known was that there are different phases of matter so we can actually take a gas and cool it, it will condense, make a liquid, we can cool it and make a solid. So a way to achieve colder and colder temperature is to take a gas and liquefy it essentially. And also it became apparent that this game was very important because it became clear that the thermal disorder was actually masking perhaps the fundamental properties of matter. So there was something to gain by cooling gases. So there was some kind of race which started. One of the major racer was Faraday at the Royal Institution in London. He liquefied ammonia and chlorine, reaching very cold temperatures. So the technique became standard. One liquefies one element and then uses that to cool down and then help liquefying another in a cascade process, all done with devices consisting of glass and low pressures and things like that, which actually are pretty dangerous because they easily break or explode on your face. So various labs were involved in this race, from Paris to Geneva to Krakow. So at some point, oxygen was liquefied, and then even nitrogen, so the major components of air, became liquid. So there was one gas left, which was hydrogen, and that proved harder. And the person who succeeded in liquefying hydrogen was called James Dewar. Like Faraday, he was at the Royal Institution, and he was quite a character. He was a very bossy character. I think he lost some assistants or made them blind in pushing them towards achieving lower and lower temperatures with these slightly dangerous glass devices. He managed to liquefy hydrogen, and so he was very proud of that. And at that point, he thought he had won this race because all known elements had been liquefied. He also invented something which was pretty useful in practice, which is essentially vacuum flask. So, and it is used by everybody. It's used also by low-temperature physicists routinely for example, to contain a liquid nitrogen or liquid helium. It's simply two vessels with a vacuum in between, and of course, it's a good idea to coat the inner vessel with silver, for example, to reflect radiation and reduce the heat losses. But there was a problem. The problem was that at some point in the late 1800s, astronomers looking at the spectral lines of the radiation from the sun discovered a new element, which was called helium. And then helium was also recovered on Earth, so we had samples of helium, and I think the first came from Czechoslovakia or Eastern Europe, essentially mineral samples from radioactive materials. And the person who actually had these samples was somebody called Ramsay at the same institution. Now, Dewar actually was not in good relations with Ramsay, and that did not help him, but the race had restarted because still there was this new element, this new gas, to be liquefied. And then another player came into the game. And this other player was a Dutch physicist called Kamerlingh Onnes. You see the picture here. And here he is together with some colleagues. I think this one is Lawrence. I recognize him from other photos. He has a beard like that. So another Dutch physicist of the time. Now, Onnes had a very different approach. He was very different from James Dewar. He was really the father of modern big science. For example, he thought that in order to liquefy helium, which was now the aim, he had actually to put together a very powerful team, and he set up, for example, a glass-blowing school in Leiden, where he worked, to produce better and better devices. And so he wanted also the best electricians, and so on. So assembling very large teams for reaching the task. So it was not actually, he was not as bossy as Dewar, or essentially trying to be like a lone physicist, but was building a large enterprise. And eventually he succeeded. And of course it helped that he had access to helium, which James Dewar did not at some point because of his relations with Ramsay. So in 1908, he succeeded after years of effort and made liquid helium. So that was really, it's considered nowadays the birth of low temperature physics. But actually it was the arrival point of essentially 1 century of attempts. Now, few years later, in 1911, he also did something else for which he won the Nobel Prize, by the way. So actually, he was wondering about electrical conductivity. He was wondering whether he knew that it decreased the electrical resistance of a material would decrease if we lower the temperature, and the question was whether it would go to 0 smoothly or settle to a constant, perhaps because of impurities or things like that. So he did an experiment, and he found that actually what he found with mercury, and he found that at some critical temperature, the resistivity dropped to 0 as far as he could detect. So that was really another big date, because the discovery of superconductivity made clear that essentially low temperature physics was meeting quantum effects. Now, Honest is not very famous, and I don't understand why, but it is so. And I was very pleased some years ago when actually going through Schiphol, which I tend to do often. For example, I'm here via Schiphol. I found this plane of KLM named after him. It's nice because I think most people don't know him, despite having Honest having won the Nobel Prize. So he deserves that at least. And also, before I finish this, I would like to remind you that there have been many applications of all these technologies and the physics which were understood during these rays. Really, it changed the way we live. Now, liquid helium, being liquid at temperatures of about 4 degrees Kelvin, is the only available practical coolant. If you want, for example, for a solid-state physicist, you want to cool your sample to such temperatures, you need liquid helium. So we find liquid helium in various systems. If you're an astronomer and you're interested in infrared astronomy, you have to put liquid helium in your satellite. And here I have a photo of the IRAS satellite, and it contained more than 700 liters of helium, and when all the helium boiled off, that was the end of the mission. Here there is another photo of a scanner used in hospitals. So here inside, here the patient is on this bed, goes inside. I've been once there, it's quite claustrophobic. So around you there is actually a magnet to do the nuclear magnetic resonance scan, and to cool the magnet you need liquid helium. And here there is a striking example of the use of helium as a coolant. I like this photo because I like to go there, that region up there. So you see Lake Geneva here. In blue, you see the city of Geneva. You see this white stripe here is Geneva's airport, the Alps down there. And this red circle actually marks where the Large Hadron Collider is, about 100 meters below ground level. So it is the largest particle accelerator. And it's 27 kilometers long. Now, there are big magnets. I think there are 8 Tesla's magnets driving the two particle beams before the collision. And the magnets are superconducting magnets. So there is liquid helium going through pipes to keep them cold at 1.8 Kelvin. So that's below the lambda point. So we have superfluid helium all along this section of this loop of 27 kilometers. Actually, it's divided, I think, in 8 sections. So it's not true that it is a single fluid, 27 kilometers long. But perhaps it's the biggest quantum system I can think of. And I also want to stress that the particles have to cross the border between Switzerland and France twice as they go around from Geneva, then into France, and then back into France and Switzerland again. But there are also more practical applications, starting from the flask, the thermal flask of James Dewar, because the techniques which are developed in these rays became very important for food. So really they opened, for example, the American West, because the ranchers in the Midwest could actually kill the cattle, and then the meat was put into refrigerated trains which could travel to the big cities in the east and things like that. So refrigerators and keeping milk or fish, air conditioning became available because of essentially spin-offs of this technique. And here, this person must be remembered, Carl Linde. He was a big industrialist who started this industry of the cold. On this slide, I've put some milestones to remind you of essentially the important steps in this development of low temperatures. So we start from the freezing point of water, 273 Celsius, and we cool down. So we go to about 90 Kelvin. Sorry, 273 Kelvin. We go to about 90 Kelvin. There we find the superconductor with the highest critical temperature. Essentially, they are ceramics. Then about 77, 80 or so, we can make air liquid, oxygen, and then nitrogen become liquid. But of course, if we continue, then we have solid oxygen and solid nitrogen. If we need then to go down to about 14 Kelvin to get hydrogen to become liquid, and then there is a big step. And now keep in mind that as you lower the temperature, things get harder and harder. So this scale seems linear, but actually it's not. You must think of that as logarithmic in the difficulty. So the step indeed from nitrogen to hydrogen was a very big one historically, and a very difficult one was from hydrogen to helium. And then we have superconductors. You see, as soon as liquid helium was available, superconductivity was discovered. Now, the cosmic microwave background radiation is only about 3 Kelvin. So when we pass that threshold, we can claim that here on this planet, this little bit of universe, well, we've made actually perhaps the coldest region. And we reach this temperature, which is the so-called lambda temperature, the temperature at which we're going to see liquid helium becomes a strange fluid, superfluid. There is another isotope of helium called helium-3. I'm going to describe it in a moment. And that becomes superfluid in the regions of the millikelvin. And then there are atomic Bose-Einstein condensates, and critical temperatures tend to be something like about 100 nanokelvins or so. And of course, we cannot reach 0. So this has been essentially the progress. And before I finish, I just want to make a remark. So it's true that as we lower temperature, we make more evident what are the important properties of matter. But actually, thinking back, what really matters is not the absolute value of the temperature, but what's the relative value compared to some fundamental temperature. For example, the Fermi temperature or the lambda temperatures, TC for short. For some systems, which some of you are very familiar, for example, polarity condensates, the critical temperature is actually room temperature. If you're interested in neutron stars, well, it's actually extremely hot. It's, I don't know, can't even imagine a temperature of 10 to 11 Kelvin. So it's T divided by Tc which matters. So to say that this is the history of low temperature physics is correct, but perhaps we should use another term, call it low entropy physics. And finally, I want to say that hereafter I'll try to concentrate on the few systems, particularly helium-4, helium-3b phase. I'll tell you what it is, and some atomic BECs, because I'm going to tell you about the turbulence, and those are the systems for which we know more. Okay? So at this point, I'm ready to describe quantum fluids. So what are they? In Leiden, after liquid helium was made in 1908, of course, there was much activity in measuring the properties of this new fluid, this new liquid. And it became soon very apparent that it was a strange liquid. It had very, very strange properties. The one which is actually very visible is this. Imagine you have a Dewar, a thermal flask made of glass, so two glass containers with vacuum in between, and you pour liquid helium inside. So liquid helium is transparent, the same index of refraction as water. It's about 1/6 the density of water, so it's somewhat light. And you cool it because you pump the vapor above the liquid. So it reduces the pressure, reduces the temperature. So the helium boils. So you see here a photo of boiling liquid helium as it cools. But it's very visible that at some point, when the temperature crosses a critical value, which is nowadays called T lambda, this temperature, then the boiling stops. And some of you must have seen this because it's a typical demonstration which we do in the labs. So there is this sudden moment at which the helium becomes quiet suddenly, so stops boiling. So this is one of the many effects which intrigued people in Leiden at the time and also in other labs. So very strange properties. They are often referred to as mechanical thermal properties. I'm not going to describe them, but this is actually essentially the signature of something important happening. Why this? Just say a few words about this. Well, at this point, we have a quantum fluid, and there is essentially this fluid here has perfect heat conducting ability. So it cannot boil because we cannot set up a temperature gradient in between two regions. So it is quiet. Now, by the way, this temperature, 2.1768, by definition, it's essentially the temperature scale is built to have this value. It's called Lambda Temperature, a strange name, because of the shape of the curve, specific heat versus temperature. So it's a historical name. Now, to appreciate liquid helium as a strange liquid, I want to compare it to any other substance. For example, nitrogen. So you see here the pressure temperature diagram. Think of the pressure scale as logarithmic. So we recognize different phases. So there is a gas, for example, there is a liquid there is a solid, there is a critical point. If you go higher than the critical point, then you have something which is not a liquid nor a gas, it's some kind of strange fluid. There is a triple point. So that's quite important because it can be used to define temperature. So you can create a situation in which you have, for example, water in equilibrium, liquid water in equilibrium with vapor and ice. So a triple point. But for liquid helium, this phase diagram actually is quite different. There is no triple point. Some people like to describe liquid helium as some kind of gas blown up by the zero-point motion, which is somewhat true. So you see that, first of all, if you start from the gas and you simply cool it by reducing the pressure, you move along this line, which is called the saturated vapor pressure curve. You can actually go down to zero smoothly without reaching a solid first. That is strange. Indeed, to make liquid helium solid, you need to pressurize it quite a lot. You need to apply about 25 atmospheres. So that's a lot. But you can make it solid. The liquid phase can be also divided into two parts. Now, these two liquids have been called helium-1 and helium-2. So helium-1 is the liquid helium above this critical temperature, or lambda temperature, which is this boundary which bends slightly up and to the left. And helium-2 is actually what we refer to normally as superfluid helium. So the interesting quantum fluid. So hereafter, when I say helium, I shall refer to this yellow region, the region where quantum mechanics rules the motion of this liquid. And but do not discard liquid helium-1. It's quite interesting, actually, because the extreme low viscosity of helium-1 allows experiments at unusually high Reynolds or Rayleigh number. So it's quite useful in fundamental physics. But this is not the entire story, because if you're not familiar with this, then you may get confused. Helium-1, helium-2. There is also helium-3 and helium-4. So which is which? So I want to make sure you follow. So the helium is the second element in the periodic table after hydrogen. We have helium. There are 2 protons in the nucleus and 2 neutrons. So there are 4 particles in the nucleus, then your 2 electrons. But there is one isotope which is rare, really. It's called helium-3. 3 because the mass is 3 rather than 4. Okay? Now, helium-3 is actually quite different, but it's part of the story because it's a quantum fluid. However, it is actually fermionic because the 3 spin 1/2 particles there. It can become superfluid as a superconductor, essentially by pairing 2 atoms of helium-3, you get a Cooper's pair. So if you compute properties like the quantum of circulation or other properties which are interested interesting from the point of view of the quantum turbulence. You have to remember that the mass of the relevant boson is twice the mass of helium-3, and each helium-3 is 3/4 of the mass of helium-4. Now, this is the phase diagram of helium-3. There are actually two liquid phases, the A phase and the B phase, because it reacts to the magnetic field, to an applied magnetic field in a very interesting way. But I'm not going to discuss this. So I'll disregard the A phase because the evidence about turbulence which interests me is mainly in the B phase. Vortices in the A phase are quite complicated. You must keep in mind just two things. One is that the critical temperature corresponding to the lambda temperature in helium-3 is much lower. It's 1,000 times lower. We are talking about millikelvins, and that makes things much more difficult. As you lower the temperature, things get more difficult. You need to essentially to have in your hands a dilution refrigerator to produce these low temperatures. The second is also the cost of helium-3. So I remember when I was a student, I was not actually particularly interested in the budget of my boss, but at some point I worked out that the cost of helium-4 was like beer, and helium-3 was like whiskey. Nowadays, things are, I think, much different, but I don't do experiments any longer. And for some years, actually, it was almost impossible to get hold of helium-3. There was a total shutdown because the use of helium-3 to detect bombs or terrorist activities, essentially the market was closed. Fortunately, it has reopened. The other thing to notice is that you can make helium very, very pure, pure of helium-3. Now, most pure than anything else. How do I explain that? Any substance, if you are a condensed matter physicist, you study any material, you will have impurities. Now, a very simple way to get rid of impurities is to freeze them out. So imagine you have this room, for example. There is air here. Suppose we put liquid nitrogen or liquid helium in the rooms nearby. So this ceiling becomes very cold, the floor becomes very cold, the walls are very cold. So what will the atoms of nitrogen and oxygen in this room do? When they hit the walls or the ceiling or the floor, they will just stick there, freeze and stick. So you can freeze out all other impurities, and there is actually a small amount of about 1 part in 10 millions of helium-3 in a pure helium-4 sample. But you can make it even more pure up to this kind of level of purity. So this is considered the most pure substance, microscopic substance you can create. In fact, it is very expensive. Okay, Bose-Einstein condensation is what I want to remind you next. So I assume that you know most of it. So just for safety, I just give some simple ideas, and there will be lectures on the topic, I understand. So I said that in Leiden, it became clear that something strange was happening in liquid helium below about 2 degrees. And in particular, the quantity which was measured was the specific heat. The specific heat is quite important because it tells you essentially how many degrees of freedom a substance has. So if energy actually spreads over the degrees of freedom, the specific heat will measure the number of degrees of freedom. So these diagrams are kind of experiments done in the 60s of specific heat versus temperature. This is the experimentally observed behavior of the specific heat. So you see a spike. Now this spike, with a bit of imagination, has the shape of the Greek letter lambda. That's why people called lambda point this critical temperature. Now on the axis, we're marking the distance from the critical temperature. You may ask, oh well, is the spike really a spike? What does it go to infinity? Yeah, you can actually do better experiments, controlling the temperature of your system better and better. So on this scale, you see the degrees. In the second graph, you see millidegrees. Okay, so that's millikelvin scale. And the spike is actually self-similar. It's the same spike. And here you have microkelvins. And see, it's still a spike, although the arrow bars become bigger. And that, does it go on forever? Well, in principle, unfortunately, you have to stop measuring it because at some point, for example, there is a gravitational correction. To measure the specific heat, you measure the temperature change induced by a essentially heat which apply. And if you have a sample and you measure the delta T across the sample, the height of the sample actually will involve a change of temperature because of the change in pressure. So the height, you know that a liquid has a pressure and depends on the height. So in the Earth's gravitational field, there will be a pressure drop simply because of the geometrical height. And that will shunt the spike. You can make your layer smaller, and that will help, but you cannot make it too small, then you essentially the healing length in quantum behavior. So there have been actually better experiments done in space, for example, to eliminate this essentially shunting of the spike. But even in space, on the space shuttle, there is microgravity because collisions with micrometeorites, etc. In any case, it was known to Fritz Landon in the 30s that this figure is from his paper, that the specific heat of a Bose gas had some kind of, not spike, but cusp. And that actually made him to think of a possible connection between superfluidity, which became known exactly in the same year, 1938, the strength behavior of liquid helium, and Bose-Einstein condensation. So now, the Bose-Einstein condensation, you know better than I do the story. So it was an idea, essentially, which started in India. There was a young physicist called Bose who thought of to a system of bosons as you cool them. And a simple way to put it is to remember that each particle has a de Broglie wavelength. And if you have a gas of such particles, you can relate the energy up there, the average kinetic energy to the temperature times Boltzmann constant. So you find that this de Broglie wavelength becomes longer and longer if you reduce the temperature. And the question is, what happens if you reduce it to 0? So this is relevant particularly for bosons because they would like to pile up into the lowest energy state available, unlike fermions. And so these two people worked out what happens, and they realized that essentially when the spacing of the particles is comparable to the de Broglie wavelength, which you achieve by reducing the temperature, then you essentially get some kind of microscopic wave function ruling the behavior of matter, and you have Bose-Einstein condensation. But that was achieved only in 1995, so many, many decades after the original work of Bose and Einstein. So in between, there was these decades in which the examples of Bose-Einstein condensation came from low temperature physics, superfluidity, as Landon pointed out, and also superconductors, etc. So only in 1995 we had the Bose-Einstein condensation as Bose and Einstein actually had in mind, in a simple fashion. The difference being that liquid helium is not a very tenuous, weakly interacting gas. It's liquid, so the interactions between the bosons is strong, and that complicates things a lot. So let's go back to 1938. So that was the year when actually there were two fantastic papers in Nature at the end of the year, one by Kapitsa, one by Allen and Misener, essentially making the same discovery. So Kapitsa was first, so he got a Nobel Prize. So he realized that the liquid helium can flow without viscosity. How did he measure viscosity? He made it to flow in a slit. So this was a picture he set up. So you see like this column of liquid helium flowing then out here in between these two plates pressed together. And he induced what would be the viscosity of this liquid. And how do you do it? Well, you know that if you have a channel flow, say moving along X between two plates, so the of separation 2D, okay? Then we have a profile, which is this parabolic profile. And here the liquid moves to the right because there is a pressure gradient. So the pressure is higher on the left than the right. So you can relate the pressure gradient to the mean velocity, which you can detect. And what is in between? In between, there is the viscosity coefficient. Now, since this viscosity proved to be very small to detect, indeed in helium-1, above the lambda point, is already 2 orders of magnitude less than water, it's convenient to make the spacing between the disks, the channel D very small, to essentially to bring out the largest delta P change in pressure you can. And you see experimental results showing that this pressure gradient essentially becomes vanishing if the velocity is not large enough. So we have this idea of a flow without viscosity, superfluid. So, and the name actually comes from the name which existed already of superconductivity. The name was already established. However, it must be said that things were not so simple, because if one, for example, measured the viscosity of helium by oscillating a small disk, so essentially a torsional oscillator like this, one got a finite value of the viscosity. So this problem was actually, this paradox, was understood and clarified by Andronikashvili, a Georgian Russian physicist, who built this strange torsional oscillator. So it's a pendulum consisting of a stack of disks. Now, he actually carefully chose the separation between the disks, and he measured essentially the damping of this pendulum. So he put it in oscillations and measured the time it takes for the oscillation to slow down to 0. So, what essentially the experiment says? Well, the experiment says that at high temperatures, there is a fraction of the liquid helium which remains trapped in between the disks because it is viscous. And therefore, the momentum of the angular momentum, which is actually within this oscillator, actually is large. But if you lower the temperature, less fraction of the liquid helium remains in the disk, can slip, essentially having no viscosity back and forth. So that was the experiment which gave Landau and Tista independently the idea for the two-fluid model. And what is the two-fluid model? It's the original model of liquid helium in which we think of this system as made of two fluids which penetrate each other. Okay? So their proportion depends only on temperature. And so here I compare the fraction of atoms in the ideal Bose condensate, an ideal gas which is Bose condensed. You see there is a famous simple law relating the fraction in the ground state to the total number of atoms, and what happens in liquid helium. So here I'm plotting the superfluid fraction, rho s divided by rho, the fraction of superfluid to the total density of the liquid helium, the amount of mass per volume, which is rho, and they're very similar curves. So they go to 0 here at the critical temperature, and then, of course, as you lower the temperature, this superfluid fraction or condensate fraction will increase and become 100%. Now things, okay, it's not so simple. Here there is a distinction to make. I said liquid helium is a liquid, not a gas. So actually the superfluid is not the same as the condensate, but I'll leave this subtle thing aside. There is one thing which is practical to remember from the point of view of the turbulence, that this curve is much steeper than that. So if you actually, remember the lambda point Tc here is 2.17 Kelvin. When you cool your system below about 1 Kelvin, essentially you have a pure superfluid. Okay? And that is important because it means you can achieve a significant superfluid fraction without actually going into the very, very high costs of producing very low temperatures. So without a dilution refrigerator in practice. So this is the two-fluid model. This is the two-fluid model, and this table summarizes the main properties. So, so we think of the helium consisting of these two fluids. We call them the superfluid and the normal fluid. So we add the densities, and we think that each component has its own velocity field, not only its density field, but also its velocity field. Now, the entire heat content of the liquid is carried by the normal fluid. So the entropy of the liquid belongs to the first row, the normal fluid row, and also the viscosity belongs to the normal fluid. The superfluid carries no entropy and no viscosity. Conceptually, it is actually the ground state. So if you remember the definition of entropy in statistical mechanics, it's log of 1, which is 0. So in this model, which was developed by Landau, we have then a set of equations for these two fluids. And this set of equations, which is written here, at least for low velocities, is able to explain essentially most phenomena which were observed, provide most because there is a caveat, provided the velocities were not enough. So let's describe these equations, keeping in mind this useful diagram, which gives the relative proportion of normal fluid and superfluid. So you see, first of all, there is an equation of conservation of mass. So like the continuity equation in classical physics, the rate of change with time of the density. We have the divergence of the current, the mass flow. But rather than simply a density times a velocity, we have a current which includes the two components. So rho n Vn and rho s Vs. So conservation of mass. The second equation has to do with essentially, it's the same equation for the entropy. So we see that the entropy here is carried only by the normal fluid. So there is a Vn which is there. Then we have two equations, which are equations for the momenta of the two fluids, the normal fluid and the superfluid. I've written them, linearizing them. So I've thrown away essentially the various terms which are quadratic in the velocities. There will be one on the left-hand side, the material, essentially at the left-hand side there should be the material derivative, which includes not only the partial derivative of the velocity with respect to time, but also v dot grad v as a term. And at the right-hand side, there should be like a gradient of a relative velocity of Vn and Vs. But I'll leave that aside. So for small velocities, this is still correct. And you see essentially this equation of motion for the superfluid fraction. You see that not only there is a term which accelerates the superfluid, which is caused by pressure gradients, but also by temperature gradients. The equation for the normal fluid is similar. Notice the change of sign here. The same term, but with different sign. And we must take into account the fact that the normal fluid contains the viscosity of the liquid. So this second equation really looks like a kind of slightly linearized Navier-Stokes equation. And the first equation is essentially the Euler equation after removing the v dot grad v term. Okay, so these equations were actually accepted, became very popular and used because they were able to explain all these phenomena found in Leiden and other labs after the discovery of liquid helium. But they were significant because they predicted some new phenomena which are peculiar to liquid helium, which are referred to as second sound and thermal counterflow. Now I see that we're at 10, almost. So perhaps this is a good time to take a short break if you want to stretch your legs a moment. And we'll restart again in 3 minutes, 5 minutes. Any? Yeah, okay. Okay, so you see the computer thought of that for you, switched off automatically. So we'll meet again in 10 minutes, and we'll continue after using the two fluids equation. Yeah. No, coffee is... oh, there is always coffee.